Hello everyone and welcome on today's video. My name is Wouter Peer and I'm the founder and main developer of GHEtool Cloud. And I'm really happy that today we will be releasing again a new feature into the tool. Now today it's a rather small feature related to hourly loads. We will cover it in a second, but it will have a big impact in how you can use GHEtool Cloud, especially in the feasibility study phase. So let's jump right into it. Now, as you know, currently I called it problem, but it's a little bit a challenge. GHEtool has very powerful methods related to the combination of active and passive cooling. You can simulate up to 6 different hybrid systems in GHEtool. You can optimize for maximum energy and power, etc. So these are really powerful methods that really level up your geothermal design. But the problem is that they all require hourly loads. So we need an idea on when the building needs heating and cooling for every hour in the year in order to run the methodologies behind these more advanced methods. And the challenge is that this type of data is often not available, especially not in early design stages when these concepts typically are decided upon. So that's a little bit the problem. We have powerful methods, but at the moment when we need them, we don't have the information. So that's one challenge currently, and another challenge has to do with collective systems and simultaneity. Now, if you have not watched a video on simultaneity, it's linked in the description below, but to summarize, when you have a collective system, for example, you have 20 apartments connected to a single bore field, the peak power the bore field will experience, is smaller than just the sum of the peak demands of all the apartments. And this is simply due, as you can see here, and this is due to the fact that users have different behavior. Not all of them shower at the same time, not all of them heat their apartments at the same time, the orientation of the apartments may be different. So the peak power is spread out, which you can see on the figure below, which is based on a research by Winter et al. The more users you have, the lower your simultaneity factor, and hence the lower the peak power that will be on your bore field. Now, that's one side of the story. The other side, of course, is, okay, if we lower the peak power, this peak power will occur more often. And if we have, for example, 80 kilowatts of heating demand and we install only 60, this 60 kilowatts will run more frequent than the 80 kilowatts. So that's a big challenge also related to these collective systems, the peak duration, and this is also something you can solve when you have an hourly demand profile. So both problems related to the advanced methods and related to collective systems all come down to, well, we need hourly data to run these simulations, and it's not available. And that's why today we release into GHEtool Cloud the hourly load profile generator. Now, typically, as we discussed earlier, when we talked about hourly loads are created based on dynamic simulations where you need quite a lot of building information, you need a 3D model, and it's very time consuming and very costly. Now, we created a method for you that you can actually create an hourly load profile based on just an estimation of the yearly heating and cooling demand, which you always have to do. An estimation on the peak heating and cooling demand, which you always have to do. And then we added another option, which I will discuss in a bit, related to the installed heating and cooling power. So based on these inputs and a weather file, an EPW file, or you can also enter your location and then we will extract the information from there, we can create for you an hourly profile. Now, the way we do this is by assuming that the heating and the cooling load is proportional to the outside temperature, which is a reasonable assumption because when are you going to heat your building? When it's cold outside. And when are you going to cool your building? When it's hot outside. And the hotter it gets, the more cooling you need. So the heating and cooling load is proportional to the outside temperature. And the way we approach this is by using the same idea as as with the hourly degree days. So what we say is, okay, we have our outside temperature, which is the blue line in this case, and we set the threshold, and below this threshold we will heat the building, and the colder it gets, the more heating we need proportionally. And the same is true for cooling, but it's the other way around. And we assume a certain threshold, and we get an hourly profile based on this. What we then do is we rescale this hourly profile with the energy demand that we got. So we know that the area under the curve, which is basically the energy provided to the building, is the same. It's exactly our energy demand. And then what we do is we check if the peak power of this profile that we scaled, if it's equal to the peak power that we said the building needed. For example, there was a static heat loss calculation, and well, this is the peak power we actually need. So we're going to check whether the peak power from our generated load is equal to the peak power we set manually. And if it's not the case, what we're going to do is we will reset or choose another value for this temperature threshold, so that when we rescale it afterwards, we end up with the correct peak power. So the way you should think about this is, if we said, okay, for example, we set it to start heating below, let's say 18 degrees, we rescale it and we end up with a peak power that's too high. Now this means that basically all our heating was cramped in too much time. And when we lower the threshold, say, okay, let's not start heating at below 18, but let's start heating below 17, there will be more times when there is heating demand, of course, because we lowered the threshold. But this also means that if we rescale the whole profile, our peak power will be smaller, because now the energy is spread out over more time. And that's the way how we cope with this, or work with this methodology. And once it's equal, we can actually say now it's done. So this is how you would do it for a single building. But for collective buildings, we have this simultaneity where, for example, not our installed peak power is not really our peak demands. Because, as we said, depending on the orientation, etc., the resulting peak power for the collective system is smaller than the sum of each individual building. And with these three steps, you get the profile, the theoretical demand profile of the entire building. But it's not necessarily the profile that will actually be delivered to the ground, because our installed power can be lower. And that's why we check, well, if our peak demand is bigger than our installed power, so if we have a demand of 80 and we have an installed power of 60, yeah, then we need to change our profile again. And what we then do is we start with our profile, but we top off the peak powers, and we take this excess energy and we spread it out in time. So if you, for example, have, let's say, a 10 kilowatt peak, but you only have an 8 kilowatt heat pump, yeah, then you know that there is 2 kilowatt hours, that cannot be delivered, because your peak power, your installed power is not big enough. So what we then do is we say, okay, this 2 kilowatt hour excess energy, we divide it by 2, and one will be delivered an hour before and one will be delivered an hour later. And by doing so, we are doing actually what's happening in reality with the simultaneity is that different users start at a different time and the load is just spread out, increasing the peak duration and increasing the accuracy of your simulation. And when we do this, the simulation is done. So this is the algorithm behind the method. I suggest we jump into GHEtool and I show you how easy it is to do this for yourself. So here we are in GHEtool Cloud. I created a new project. We will just work with the default values for now. Let's go to the thermal tab. And as you can see, we have here now a button that says create hourly load. Now, just to show the difference, we're going to simulate this scenario. So this is the simulation with the monthly profile. Now we're going to duplicate this scenario and I'm going to call this I am going to call this scenario 2 hourly. Let's go ahead and rename this. Go to thermal demand. I say, well, let's create an hourly load. So what this does is it pops up a new tab where we have a couple of input information. First of all, we need to have a weather profile. Now you can upload a weather file, but what's perhaps easier is that you can just say, what's your location? Let's say Frankfurt. In Frankfurt, where there I'm going to use the location, and then it will automatically create an EPW file for this location. This is based on the European project PVGIS. It's really easy. And then you can select the type of system you have. So we have the option to have a single user or a single building or a collective system. And the difference is that if you have a collective system, you can say, well, I have 20 buildings, for example, and it will calculate the simultaneity for you. Now, in our case, let's just work with a single building. The flow is the same, but it's the easiest to compare. So we have our peak heating, peak cooling, and the yearly heating and cooling demands. And the max installed heating and cooling power is by default the same as our heating and cooling demands. Let's go ahead and generate an hourly load, and tada, here we have it. This is the hourly load profile, which has the same peak heating value, which will be, perhaps we can just zoom in, show it, it will be 15, and the energy below will be also exactly what we set it to be. So you can download this as a CSV, which can be useful for all sorts of things, but you can also load it. Let's go ahead and send it to the server, and now it will perform the same calculations as before, but now with the hourly load profile. So this is the result we get. Nothing too spectacular. We all are familiar with this now. So the advantage of having now an hourly load profile is that basically all our advanced methods, like the optimized load profile, like the combination of active and passive cooling, now all became available. And when we in the future add variable flow rates, etc., this all will require hourly load profiles. So now with the same type of input information, we ended up with a more detailed profile, which has the same characteristics, which has a realistic behavior because it's based on the outside temperature. And now there is way more possible. So let me, just to end this video, show you how it is if you say limit peak power. So imagine you say, okay, let's go edit this profile, go back. You say, okay, we had a peak power of 15 kilowatts, but imagine we only install, what should we say, 12 kilowatts. We can generate an hourly profile again. It looks the same, but as you can see here, it's topped. So in this case, instead of going to 15 kilowatts, it's spread out this load. And when we use this hourly load profile, we simulate it again, you can immediately see the effect it has on the design of your system. So here we went down to 5.07 degrees. Here it's 5.69 degrees, due to the fact that indeed now our peak power is topped off a little bit, and we're working with a longer peak duration instead. So this is really powerful, this method. You can play around with it. You can see what the effect is of oversizing your heat pump, undersizing your heat pump. Now, of course, this is based on an assumption. It's still better to actually simulate your building to take into account real occupancy behavior. Perhaps some days of the week your building is not being used. That's all information you can take into account in a dynamic simulation. But when you're working with just estimates as you're doing with monthly load simulation, you can now do the same with hourly loads, but then you have the whole range of advanced methodologies at your disposal. So I hope you found this video interesting. You've requested this method for quite some time now, and we are finally able to bring it to you. If you have any more ideas about articles, methods, please let us know. We're happy to work together with you, our community, to give you the best geothermal design tool that's out there. I hope I see you in the next video, and take care until then. Bye.